In this video, I want to continue talking about how to write the formulas for ionic compounds, and I will use the periodic table that I have sent you uh, to use as a reference to memorize the symbols and the charges. Just, I guess, a small note. Sometimes people say oxidation numbers, sometimes they say charges. It's actually worth noting that what we're talking about is what the elements will do potentially. I mean, to begin with, they're actually neutral. They don't have a charge. This is, when we say oxidation numbers or charges, what we mean is the charges that they will have when they have reacted with something else. This is something we'll talk about a lot more in Chapter 6, but for now, I just wanted to sort of clear that up because you'll hear me use those words interchangeably. So the oxidation numbers are in this periodic table are up here. So for example, we see with copper that it has oxidation numbers of +2 and 1. And this table is organized so that the first number is the more common oxidation number. Right? One of the nice things about group 1 and group 2 is that they only have one possible oxidation number, so that makes them a lot easier to learn. Also, I should mention, and just make sure that you understand this, the elements that you need to know that you're responsible for are the ones that are in red. So there are lots of elements, but you only are responsible for the ones in red. Okay, let's take a look at another set of numbers, another column that you're responsible for. So if we go over to column 13, there's another way to designate these columns, and I'll talk more about where that comes from later, but for the moment let's just call this column 13. And we see that in column 13 there are two elements that you need to know, boron and aluminum, and they too only have two possible charges, so that's good. Then if we go over one more to column 14, we see for column 14 things change a little bit. So carbon can have either a plus or a -4. What this means is that depending on what it reacts with, carbon can either gain 4 or lose 4 electrons. Silicon is similar, and germanium is a little different. So germanium can lose 4 or lose 2. So although the elements are similar within a column, they do change as you go down a column in some cases because the electrons are further from the nucleus. You have more electrons, more levels of electrons, and they're further from the nucleus. If we go to column 15, we see a similar sort of pattern. So we have nitrogen, which is -3, phosphorus, which is -3, arsenic, which can be 3 or 5, and then we have antimony, which can be 3 or 5, and also bismuth, which can be 3 or 5. So what's happening over here, at least for the first two, is that we have moved into a situation, sort of made a transition between losing electrons and gaining electrons. So as you move over, there's a greater tendency to gain electrons. The atoms can still lose electrons, but it's just that their most likely state is to have lost electrons. So let's use this information and write another formula. So let's say that we would like to know what the formula would be for a compound that forms between boron and fluorine. So we have boron here, which is +3, and fluorine over here, which is -1. Okay, so we have boron, which we said was +3, and we have fluorine, which is -1, and in order to balance the charge, we just put a 3 there. Okay, now I want to talk about something a little bit different, sort of a variation on this idea, and to do that I want to go back to the periodic table. Okay, let's use iron as an example, and look at what we have with iron. It's a little hard to see on this table, and if you have your own table that you've printed out, then by all means look at that. But if you look here, you can see that iron has a +3 and a +2 charge. So what that means is there are really two different things that iron can do. So let's talk about that some. Let's say that you are trying to, for whatever reason, you're told that you need to write the formula for iron chloride. And so you say, okay, well, I'll try that. So here we go. There's iron. and there's chloride. So I know this much, but then I've got a problem because the iron can be either 2 or 3. So you're missing some information that you need. Well, obviously that's not a great situation. So what we're going to have is a system that says, depending on which form of iron we use, we're going to indicate that by putting a Roman numeral here. So let's say that we want to write the formula for iron 3 chloride, which we've already said was the common form, so we'll do that. Well, now we're in good shape. We know that we're in fact using this form of iron, so if the iron is 3, then we just put a 3 there. Well, what would iron 2 chloride be? Well, I think fairly obviously iron 2 chloride would be this. So this is just another situation, and it's how we deal with having more than one possible charge for the positive ions. For the negative ions, it'll be a little different situation. But so for all of these that have 2 or more charges, we have to use that. So look at manganese, for example. Manganese has a bunch of charges, and so we have to be careful with those. Mercury has 2 possible charges. And let me just take a minute and talk about mercury, because mercury has its own kind of special situation. So I'll sort of end this video with a little discussion of mercury. So first of all, let me clear this out of the way. Oops. So I don't know if you can tell or not, but I'm doing this on a different device. I'm using a graphics tablet right now, and I can't write as well on it as when I was using my iPad, so you just have to bear with me. All right, so here's the situation with iron. Let's just stick with the same sort of idea. Let's say that I was trying to write mercury 2 chloride. So that one is straightforward. I would write Hg, and it has a charge of +2. And the chloride over here has a charge of -1, and I would put a 2. So that's straightforward. On the other hand, let's say that I had the situation where I was told to write the formula for mercury 1, and it looks like that should be straightforward also, that it would just be Hg with a plus and Cl with a minus, and then that would be it. However, there's something a little bit odd about mercury in the +1 state. In the +1 state, mercury acts a little bit like a diatomic. It's kind of a diatomic ion. So it always comes in 2. So let's be clear what we're saying here. This means 2 mercury ions. Each of them has a charge of +1. Okay. So then over here to balance, I have to do this. Okay, so mercury is the only one I can think of where you have this situation. So just be aware of that. All right, let's end and let's just do this last little exercise. So let's say that you are asked to write the formula for copper 1 oxide. And let's see what you would do. So you look on the periodic table, you find copper, and you see that copper can be either 2 or 1. Well, okay, so that means the reason that you have to do that, or that you need to know that, is because if copper just had 1 possible oxidation number, then you wouldn't have to put this 1. But because it has 2, you have to put that. So you're going to have Cu, and I'll just go ahead and still put this up here. Normally we don't write those up there. I'm only doing that because I'm in the mode of explaining this to you. Oxygen is only -2. That's the only one you have to deal with right now. So how many coppers do I need to have? All right, I need to have 2, like that. Let's take a look. Sorry, I said that was the last thing, but there's one more thing I want to look at. One way to organize your thinking about this, sometimes you find this helpful, I kind of find it helpful. I like things to be organized and sort of systematic. So for ionic compounds, you can think about the naming system this way. So an ionic compound is going to be a compound formed between a metal and a nonmetal. And we talked about those before, the distinguishing parts of the periodic table that let you know if you're dealing with a metal and a nonmetal. So for a metal, the simplest situation is that you only have one charge. In that case, you just use the name of the metal. So that would be like sodium or barium or something like that. The other case is that you have a situation where the atom, the element, has more than one possible charge. And in that case, you have to put the charge that it actually has with Roman numerals. And I can see now that there's something else I need to explain, which is about main groups. So I will go back in a second and explain this to you. Okay, over here for the negative part, the anion, if the anion is an element, so monatomic, an element, then you just say the name plus IDE. So that would be like chloride. And then we have a situation that we haven't talked about that we'll talk about in the next video, and that's if the anion is not a single element but is a polyatomic. So we'll talk about that next. But let me just first go back while it's on my mind and just distinguish main group and the ones that are not main groups. So the main groups are the ones here that are A's. So 1A, 2A, and then over here you skip over 3A through 8A. Another way to think about it, actually this is more the way I tend to think about it, it's just this section, these are not the main group elements. So these are the ones where you're going to use the Roman numeral in between the metal and the non-metal. Okay, well that's probably a lot. That's maybe more than I intended to do for this video. So I'll stop now and we'll pick up and talk about polyatomic ions in the next video.